Hello, I'm Nissim. I'm about to start a series of videos about the fundamentals of the AI model, clip, VAE, and all the rest. You probably heard about the words, and now we are going to understand what they are. The first one is the model itself. What is a model? A model is a neural network that was trained by lots of images and descriptions. So you take an image, you give it data, you said this is a man, this is a woman, and then it start to learn about those words, about the word and the corresponding images. Now, the model itself is actually the part that take the meaning, yeah, and convert it to an image. Actually take it and convert it to an image using noise. And what does it mean? Let's see here. So I will have a simple flow without any data. Okay. So I have here the loader of the model itself. I have here the input, which is the positive, and I have the input of the negative. Now, in the case sampler is the part that actually take the model and use it. But I want to cut it a little further for you. Technically, we are starting with an empty image, and as we said, it's using noise. What is noise? Let's see here. Here I have multiple steps of the same image. First of all is the blank image, which is this one. You can see that there is nothing in the image. It's empty. It's totally empty. After that, to get a different data, different images, we can start from the same image. If we start always from this, we will get the same image each time. So we need to vary it. How we do it? We do it using a seed, noise seed. So usually we have the value here, but I want to separate it for you to give you more glance of how it looked like before you have an image. So I took the empty image, which is that. You can see it here. And I have the image after I merge it with some noise. So I took the empty, I gave it noise, and now you can see that you have another image. You see here the image. Now, this image is actually noise. You can't understand anything from it. But because the noise is different each time, it's given the system the option to give you an image and another thing. So let's change the noise here just with one number and run it. You saw that the noise change. So we have a different noise. And by the way, the numbers here are the thing that we have here, sequential number, are not meaning anything to the sequence of the noise. It's just a random a number that will signify for you that this is the same noise as before. So if I will run it now with the new noise, you say it changed. Now I will run it with the same noise, it won't change. You will have the same noise. Okay, so the model itself take the noise and by steps and algorithm that we will talk later, actually create a new image. So let's give the same number of noise here, and run it. So the noise won't change, but the image itself will change because it's now starting with a different noise. Okay? Now you see garbage. Why? Because there is no input. Also before, but it understood the input somehow. Let's give it another number. Now I got something. Okay? It's like, I don't know what it is, rocks, whatever, but it's noise. Because there is nothing here in the input. but the system can understand something from it. Let's try with another parameter with the same noise. Let's see what we'll get. Same. Okay. So let's try with another noise. The noise change here. Here it's still the same because it's the empty one. Now I got a different noise. It looks like small rocks. Okay, but still there is nothing here. Now the model tried to take the text that we are giving him. Right now we didn't give him anything. And this text, we are converting it. It's trying to understand from the meaning, from the words, and try to convert, to take the noise and make it to a new image. So let's give it a word, I don't know, window. Okay, just window, and let's run it. The noise is the same. We got a window. Okay, now let's change the noise in one number. The noise changed. And also the window. Now, if I will run it again with the same number, I will get nothing change. Okay, there is nothing to change when all the values are the same. So although it's random, if you give the same number that came in the random order, you will still get it as the same result. Okay. Now, all those numbers here will determine the outflow, the outcome. So let's change it to 25. I'm with the same noise. The same noise, but the result now, the model can work on the image a little more. Okay, so the interesting thing is that the model try to take the noise that we are giving it, and it convert and it try to make sense of it with the input and make it to an image. Now the model, all this system come with another part, which is the clip. Clip is actually the part that convert text to something that the model can use. Because the model does not know what actually large window is. It doesn't know that. But it is know some mathematical way of telling him, I want you to do something. Okay? So, how does it work? The clip itself is the text encoder, which means it's taking the text and convert it to something called embedding, which this is the final representative of this text. Now, embedding exists in many ways. Okay, it gets many input to get the final embedding. But the simple thing is that we take clip, take text, and then we get the embedding that called conditioning, which is the thing that the model itself gets. Now, how actually, I want to give you a little bit about this math. It's not complex, but let's take this large window text. Now we want to convert it to something that the model will understand, which is this is simplicity of the data. But let's say each word represented by some numbers. Okay, so the model will understand that we are talking about large window. Now each word depends where is in the sentence. Depends if it's in the beginning or the end. Depends which word come after it or before, because then the meaning is totally different. Okay? So think about long number of vector of numbers. Long amount of numbers, which can be billions of numbers technically. Okay? Here you can see that the number has 6 digits. The idea of those digits is to say larger understanding about variety per word. Okay, it's important because as the number here is more precise, the model can know more and more things and more small adjustment or small point in your input. Okay, as the model became more complex, the numbers here will be more precise. It means that instead of 0.43, you will get number which give the model more options to decide by. This is why you probably download the F8 model or F16 that will give you less memory usage. It means less numbers. The number is less precise, but your model can run on the hardware. I want to emphasize something about the clip model and the dimensions, which you don't have to know it, but it's good to understand why you can't run some models and why you have so much memories, etc., that you need to run for a specific model. Why one model is 4 gigabytes memory, the other is 10, another 15, and 124, and some that can even have hundreds of gigabytes. Okay, the idea is the amount of dimensions per model. What does it mean? Let's take for example the word window as we use now. Now, if a model like the stable diffusion is let's say the stable diffusion XL, it contains million and million of images that they trained this model. Now, each word that you are using, the text encoder, the clip itself, take this word and by the sentence and more data that it understands from it, compose a vector of numbers. So the word window will be actually 512 vector number. It means a vector is a list of 512 numbers that will compose the word window. Now, you probably saw that you use F8, which is float 8, or F16, or there are even F32 that usually you don't have the number, you just have float. The idea is that the amount of points, decimal point, the model can hold. Now, float 8 is half the memory of float 16. This is why when you move to float 8, you have maybe you won't have the full capacity of the model, but you can run it because your video card can run has a 12 gigabyte and the full model is 24, but you can't run it, so half of the model is around 12 gigabyte of memory. This is why the model moved from float 16 to float 8. Okay. Also, you have the float 32, which has much more decimal point. You see, those numbers are the decimal point. So you double the memory for each better version, which means much more data. So this number is 512 numbers list. So it's a lot of data that compound one word. Now, if you add lots of word to the prompt, you will see that it's working sometimes faster. Yeah, it means that the model has less data to work with. But if I will give it tons of data, now it needs to compose it. It might take it a little more time to understand it. But now the model has much bigger embedding to use. And if it needs more memory, I had some rendering that it ends my 24 gigabyte of memory. I'm using 4090 NVIDIA card. And it finished the memory there and it added another 30 or 40 gigabyte of memory for my normal memory to finish the job. Okay, because I gave it really big image. I upscale. I make an image much larger in pixels and details, and it took him around 1 hour to do it. but the amount of memory, it got to 60 or 70 gigabyte of memory. I even got to 100 gigabyte of memory because of the amount of data. Now, just think about it, that the latent, it means the space of pixels that we'll talk about is also bigger in memory. It means that you need much more memory to compose, the model need to compose the image. So it became much more bigger and bigger and bigger as you have more details in the memory. This is important. Those numbers are critical. So it can actually decide, but by using more and more data, how the image look like. You probably ask about ChatGPT and other sophisticated model. Now, those models has much more dimensions. The ChatGPT has thousands of dimensions, thousands per word. This is why it understands things so well. It's not just to understand something and give you an image, which is complex. I'm not saying it not complex, but to give you the right answer in words, it means that it has much deeper and deeper understanding about the word itself. So the word window, won't be 512. It will be thousands of numbers in different contexts. That each one will give it a little more adjustment about what is the context, so it can give you a better answer by the data that it has. So the ChatGPT and those crazy models are so high memory and need so much power to run because they have so much data, and they can't run on float 8 or 16. I believe they run on float 32 or 64, which in 64 you see that you have 17 digits of number after the point. It's much larger number because it has so much data that it need to collect and to hold to give you the correct answer in text. Now, in images, like in stable diffusion 1.5 or SD, you have different amount of dimensions. Okay, you have in most of them you have 512 dimension. You can have in Flux, you're getting to a little more. As you have more dimension, you have more understanding, and you need more memory to hold it. Flux need 24 gigabyte of memory of my GPU card, but SDXL need only around 11 gigabyte. SD need 5. Okay, SD 1.5 needs only 4 or 5 gigabyte of memory, which is okay for most of the devices. Okay, so we are getting the clip itself, getting the clip from this model. Now, because we load a checkpoint here, which is we loading a model, so most of the models come with a clip. Okay, the clip, we are using that clip, but I can load even, I can duplicate this one, and I can take, let's say, that model, and I can connect this model right now to here. Now, if the models are from the same base, it's supposed to work. So I'm taking this model, yeah, I'm taking the model from Delta and the clip from the other model. Let's run and see. If we get in an error, probably the model the clip is not matched to that model, which is possible. Let's see. We are loading it. Loading. The case sampler actually says, okay, I can work with that. And we get a totally different picture. Okay, let's bring back the old model, the clip of the old model, and let's run it, and let's see what happened. We get a different image, although all the parameters, the noise and everything is the same. The picture change. Why? Both of those models has a different clip. Because it's a different model, it has different data. It has different numbers that represent the final value, which is important. Okay? So now we are getting to two topics that are come together, which is the latent and the VAE. What is actually the latent? The latent is the playground where the model can play and to do whatever it need to do by taking the noise and convert it to an image. Now, as we said, we have an empty latent, which is totally clean, as you see here. Now we are taking we are taking noise and add the noise to the latent. We are manipulating the latent a little bit. This is the noise here as we had. Now the model getting the latent, adding the noise, and try to understand by getting the embedding, as we said, from the clip. The clip take the text, convert it to embedding, which is the language this model can understand, okay? And it's giving us an image. But before that, we need to decode the latent that get out of the model, and we need to convert it to an image by some algorithm. This algorithm is the VAE. Now, you can see that we are taking the VAE from that model, from that specific model, okay? And we are giving it to the decoder. It means that until that point, we don't need the VAE. The VAE is just reading the latent space that come from that model and converting it to pixels, to an image. So here we see that we are getting the correct image. But let's take a different VAE, a different one. Let's say here we are using SDXL. We are now taking external VAE for SD. It means it's SD 1.5. It's a different type of model, different type of way it's encoded. And let's give to the image, the decoder, this VAE. And let's see what happened. See, the image, the way it's decoding the latent to an image got totally messed up. You can see it doesn't know exactly how to do it. You have you can see the resemblance. You can see the window, but it's not clean. All the noise is there. It means that that VAE cannot actually read that specific model pixels. Let's take a different VAE of another model, which is SDXL. And voila, both the model know how to read the same structure of latent. It means that you can use different model VAE to read the latent of different models. Now, you have also you can even also take the specific SDXL VAE and use it independently if you need, but it's the same one that you have here usually because they derived from that one. Now, there are some pitfalls with the VAE. The VAE is not working, not all VAE of any model work with any model. If the base model are okay and they can understand it, so it's fine. But the model, when it's working on the latent, it changes it. Okay? And it prevents you from working with it with the different models, with a different VAE of other models. For example, we rendered that image here, which is okay. Now, when we are loading the VAE, for example, of the VAE of SD 1.5, and we try to render it, you saw that we are getting a noise. It means that we didn't read it correct, but it could read it. But let's take it with the Flux, for example. It's a totally different model, totally different latent. Everything is completely different on the way that it's reading it. And let's do it. Now we got an error. Okay, the model, the VAE, the VAE cannot read the latent of that model. It doesn't have the same structure, the same as we saw before, the same array vector of values that actually is a matter for the model, because the model know exactly what is the structure, what each number means, etc. And the VAE usually come with a specific type of model. This is why it's know exactly how to read the numbers, and you don't have noise, etc. But here we took Flux and we give it the latent from the SDXL base model, and we get a mess. Okay, it doesn't know how to do it. So if you want to go back, we can just give it the SDXL, and now it can read it and it will display it correctly because it can read it. So VAE come together tightly with the model and a latent. If the latent change by a model, not all other model will be able to work with it. Now, if you do want to use multiple models which are not tightly connected, like with the you want to move the image from one to the other, you must do first of all decode VAE decode, get the image, yeah, and then you can do VAE encode with the new with the new VAE. Let's say I'm taking now Flux, and now the latent that I will get from this model, let's put them together. Now the latent that I will get here is belong to the flux, to the Flux. It means that I can now use a different type of model. I use a different sampler and different method to use that image and to continue with it to a new flow. So I can use multiple model one after the other, but I must convert them, like decode and encode, to have it working together. It's important. If not, you will get the message that we just get and you said, what do you want? And I do want to show you something that we talked about. Look here. Those values are the dimensions. We spoke before about clip and the model that have the dimensions. It means that one model has X dimensions, the other has different one. Now, the structure that they're writing the data is different. Yeah, so they actually cannot read one of the other. And if they do, you will have the image that we just had here below. When we use this VAE, and you got noise. It's read it, but you have noise, so it's not perfection, it's unperfected image. So now we are getting to get deeper to the prompt area. Okay. Now the prompt, as we know from the previous sections, is getting a clip from the model that we just loaded. That clip encoding the text to embedding, which is that point. The output itself is called conditioning, but the structure that go out 2, the case sampler that the model is using is embedding. Now, why we have here embedding? Because embedding are binary data. This is not text. This is imagine that we took thousand and thousand of words and convert them to some we pre-digest them in a prompt and prepare them already for the model. Okay, so what we are doing now, we can actually take pre-prepared embedding. Let's say, for example, CXL match. You will see in a second what this thing means. And this thing treat like we get tons of other data that describe that prompt. So now the clip, the text encoder know that this is embedding, and it will encode those words, and after that it will take all the embedding here and combine them together. So if, for example, we have this window, so look what happened when we added the embedding to it. Okay, we still have a window, but that embedding is doing like a clutter, like a mess, but it still keep it. So it gave us, you can see here, different of chunks, tons of chunks. But those chunks are just like we went to the prompt and added tons of sections of words that mean that we want this chunk. Okay, now if I will remove it, I will get the same image, exactly the same image as before. And you can see that the image is not changing, like the location, etc. is almost the same. But look how it looks like now. So before and after. Okay, now the one of the biggest things for embedding is for negative. Okay, if I'm adding here embed easy negative, this easy negative add lots of goodies that you don't need to say I want blurry, I want I don't want things that are not safe, etc. So this easy negative has tons of data about what you don't want, and usually this is the common thing that you don't want to present. So let's run it and let's see if we get any other image, because we said easy negative. Okay, so it influence on the image. It actually influence and give you a different thing. It can be like lights, that the lights are not too dim, etc. And there are lots of embedding that are prepared for different tasks, for positive or negative. It's up to you. Okay, so this is the embedding. But now we have something which is more cool and fun. Usually, you want to get multiple values, multiple images, and you don't want each time come here and change window, bedroom. Okay, window, blah. You want a totally different scene. So we can do something here. We can do something very cool here. Let me show you. There is a thing that called wildcard. Wildcard means I'm going to give you a placeholder. That placeholder you can replace by random values from somewhere else in Comfy. Okay, so let's see. I'm using here, by the way, some a random a wildcard processor of Mickey. You can get it from the node manager. Okay, the Mickey nodes, a guy that make it like amazing. There are lots of goodies here. I will show you later for more. Now, what this thing is doing is giving you random values. You can see here that it has a seed that giving you different values, can be fixed, increment, decrement, and randomized. And it's giving you here the description that comes from the wildcard. Now, the wildcard is actually, you can see here, I created one. I went to a ChatGPT. I asked him to give me 50 or 100 or 10,000, it doesn't matter, scenes. To use it, you must do underscore underscore, paste the name of the file. It's a text file, which each line has a different prompt, and underscore underscore. Now, let's go to 0, just to make it clear where we are. Okay? Now, this thing, it doesn't render anything. It's just giving you a string. So I need to connect this string to my prompt. And I can't use it because I already have here a prompt. So what I will do, right click, convert widget to input. And now you can see that the text area became a connection. So I can go to the wildcard processor, and from now on, the text comes from this processor. And here you have another node that will show us what we have here. So let's run. Now we get seed 0. It means that we get one of the values from the file, and we got what we actually about to get. So you can see this amazing prompt that was generated. Okay, and the image. Okay, now if I will run it again on fix, I will get the same image. Why? Because the seed did not change. Let's change it to 1. And here below, you can see the images that generated. Now we are running now. Number 1. Now it changed. Now it's ancient oak. And we have it. Let's do another one. Let's do it with increment. I will move to the image itself, so it will be easier to see it. Okay, this is nice. Another one. And it's random. Now, if you will have 5,000, 10,000 thing inside the file, you will get each time different thing. Now combine it. With the random seed here. Let's do randomize. It means that now it doesn't matter how many images I will create, the random or the increment values here with the random of the case sampler will give me technically unlimited amount of images. Yeah. So if I will take it for randomize, now I'm technically will never get the same image again. Because why? Because as we said, we start from empty latent, but then we are giving it a different noise, and the noise is the same is the noise here, plus the different value of the random here in the wildcard, and now I will get more and more and more, and technically I will get infinite amount of images for those prompts. Okay, so the wildcard is super cool. I'm using it a lot. Now I want to show you where are the wildcard in a Comfy, and I want to show you how a file of a wildcard look like. One of those that you just saw here. Yeah, so you can see it here. this is the actual folder of my wildcard. So you can see the same name here. Yeah, the same name exists here, the same file name. Okay, I will increase the size here. Yeah, so the same file name is the same name here, or in the where you actually put the wildcard. Now, there are wildcards that are inside folder. For example, that folder that I download, I have here lots of other wildcard, like animals, bird, etc. Now, I need to set the same path to this file name from the wildcard folder. Okay? It means that I need to come, and you see, you have the cyberdelia slash animals slash cyberbirds. Now you can see here cyberbirds is inside animals, and the animal is inside cyberdelia, and that's inside wildcard. Okay, so if I want to use it, let me cut that folder, that name, and now I will run it. And we got a bird. Okay, which is great. It means that I can use any number of any combination between them. I want to show you one more thing. Like, as you saw, I can do this action. Okay, now I have two random wildcards. Okay, let me hide this one. Okay, now I have two wildcards. Yeah, and here, remember we just ran the birds. We have here the bird that selected. So now I will do it with both of them. Now I have this bird and some other things. Now it depends what the model will decide. Let's see if you have something. I don't see a bird. Okay, it's depend on him. If I will run it again, now it's a different bird. I have this one. Maybe it understands it differently, but the wildcard is important. Now I want to show you how the file of the wildcard work. So here, my wildcard. You see, this is the random subject non-people. Okay, and I have here 1,000 lines of random stuff. Okay, which the ChatGPT created. If I will show you it without with wrapping, you can see that each one is around 300, 400 characters. Okay, which is give me very detailed description of the image. Same for random subject, which include people. So I have here almost 2,000 types, and I have one that is a totally random subject, which I have another 1800. Okay, those can give me the option to create crazy thing without the need to start to think, and then if I need to do something, for example, to generate those images, I just gave it a couple of times to generate the images with different prompts. Okay, so the part of the folder is important. It took me a while to find the exact structure because it wasn't so clear. And if you are in the main folder of the wildcards, you can just use the file name. Do not add stuff like .txt or things like that. Just the file name and the folder to it. Now we are getting to the seed. Seed is, we saw it until now as the value that we are setting to get a different noise. Okay, so you remember that we have an empty latent, and we gave it a noise. So now I set the same value of noise, of seed of the noise in both of the nodes. Let's run it. So we have here noise, we have the empty latent, we have the noise, and we have the image here by the description that we added using the wildcard. Now, the numbers here are can get to infinite. Right now we have here a number of like 15 digits. The idea here to give you the unlimited options to get unlimited noises, so you will never start, the model will never start to denoising the noise and make it as image by using the binding, the positive and negative. So technically you're supposed to have unlimited variation of images. Okay, now the numbers here are, the sequence of them is not matter. The system gets the empty latent and give it a variation of random numbers based on this seed. It means that if I'm giving the same seed hundreds of times, I will get the same noise. I will never get a different image unless I will change something. It can be the prompt, it can be the negative prompt, it can be the step that we'll get to those area in a couple of minutes. Now, so if you want to know exactly how to reproduce an image, you can just select the correct seed to get the starting point of the image. Now, the control after generate, this is the word after is crucial. Why? When I'm doing fix, we have here a couple of values. Let's start with fix. Fix will give me the same value over and over, and I will never have anything change at all. So I'm now on 40. Click it again. I'm still on 40. It will never change. Now, if I will do increment, I will select the increment. It's telling me that after it finish, this is important. After it finish to generate the image, or after it select a seed, it will increment it by 1. It's not doing it before the generate, so it will show me the value that is now generating. No. So if I'm now on, I select 42, now I'm running it. I will get it for the 42, but it's incremented for the next image. It means that now that image is on 42, meaning if you want to know the number of the current, the last image generated when you are in increment, you need to go 1 back. If I will do this action and run it again, I will have 0 changes. It's the same image because we run it on the previous number. Same for decrement. It will run it. Let's go back. It will run it, and then because I have nothing to change, it reduces it to 41. Now, if you want to know the numbers, so it's good to use increment or decrement. If you use random, let's go to here. I'm again in 42. I'm running it. By the way, Control Enter will run it. So now it generated with the old number, but look what happened. It just changed it to a completely different seed number. It means that if I don't know the number, the number here that I generate the image with, it will be hard for me to get it because it's not increment or decrement. It's just random number from billions and trillions of numbers. But if you want the previous image number, you can you can get it from the old image. But if we will do save, I could get the image. Yeah, let's do it. Have a new image, save image. Okay, now I will run it with the current random number that I have. I have the 85 in the end. I get a new value for the next image, generate it. Now I have the image. Now, what was the value of the previous image? I don't know. How can I get it? I can go to the folder where I generated the image, and if I will drag it to the Comfy, what just happened? I drag the image to the Comfy. All the data about the generating of the image exists inside the image in a format that the ComfyUI added to the image as metadata. And now you can see that I have the previous number. Technically, it took all my previous, all the nodes that I had, and it inject them to the last image. So this is good and bad. It's good because I can take any image that I generated, drag it to Comfy, and I will get all the data. Also, this is the number, so I can extract it. The negative part is that anyone can get your workflow. So you need to resave it with a different software or remove it using a metadata remover called EXIF. Okay, so that was a quick tip just for the images, but let's continue. Okay, now let's go to the next part, steps. Okay, steps are the amount of time you allow the algorithm, the model, to check and denoise your values, the noise. So if you will run the image on one step, and I will make it here fix and run it. Okay, now I'm on fix, so I have the numbers the same all the time. And I will also copy the value of the seed here, so you will see the noise that's supposed to come with that image. Okay. So what we have here? We have the latent, empty latent, then the noise, and then we allow to the model to denoise the image only once, only one step. One step is nothing because it's very hard to understand the image itself. But let's see. Let's give it two steps. I will move all of those here, so it will be easy for us to look on everything in one place. Okay, this is 2. We don't have so much change. Let's make it 5. Okay, now we start to get something. 5 steps, it's not enough, but it's quite enough to see something which is visible, okay? Which is not only noise, okay? Now, if you give it 10, you allow the model before it take the before it take all the noise, it try to remove it in 10 steps. Remove it until it gets something. And you can see that we are in the same prompt, the same seed. Everything is the same. Only the steps that we allow the model to work on it is different. By the way, each step is more computation. So 10 gave us that. Let's see 11, which is one step more. It's a little different, just a little bit. Okay, if I will give it 20, okay, it's a little more different, but the image quite changed. Let's give it 35. I'm using the NVIDIA 4090, so each run is a couple of seconds. Okay, now it refined the image a little better. You can see the image here and the image here. It's a little different. It's not so different, but it's a little different. Okay, now let's give it 70. Let's see if we see any change in 70 steps. Again, each step is more computation. Each step is more hardware. If your hardware can handle it, fine. Usually people use 25, 30. I just want to emphasize what we actually getting from different values. Okay, so the image from the 20 and the 70 does not get such significant change. It gets more refinement of details, maybe a little more light, more pay attention to small details, more focus on stuff, etc. Okay, from 70 and above, let's say from 50 and above, you're not supposed to get so high differences when you render the image in the steps. Another important point in the steps are the amount of steps that the model using to generate the current step that he's working on. If you will search for clip set last layer, it means that I will set it to -2, which is the default usually. What it's actually doing, it will do in a couple of seconds. We will tell the model to generate each step, go and look on the last 2 steps. Not only one, the last 2. There are also models that can check the 3 steps or 4 steps, which is mean it use much more computation power because it need to take multiple steps, and from them it will help him to understand the next step with the noise, all the denoising, etc. So we need to connect it to the flow, and we will connect it here. Let's give the clip, and from here we are going to clip and clip. Okay, now it's in the middle. Now we will run it on 2, and let's see what happened. First of all, I will drop the step to 25, and now we'll run it to save time. Okay, we have an image. Now let's drop it to 1. I want you to check only the last step that it worked with. And let's copy it here and move the image to here. So I won't lose that image. You can see it. You can see both. Okay, totally different. It makes something else. When increase the size, it's different. It didn't use 2 steps. It used only 1 step. Okay, so that one is 2 steps. That one is 1 step. Let's see if we can get something else from 3 steps. So we change it to 3. All the data is the same amount of steps, everything is the same. Let's see what we'll get. How different is it? The red rectangle means that it's not connected to anything. Okay, now it used 3 steps to generate the images. It means that this model, the SDXL, can handle 3, maybe also 4 or 5. But you can see that it's different. It's a little different. Here is something that does not make sense because it's floating, unlike those that here we have a surface. You see? Here the sink gone, when you have 2. On 3, it's completely like you have a thing, but it's floating. Okay, like the -1 is more real for these steps. Okay, so this is about steps. So let's see the CFG. CFG is clarifier-free guidance, which is mean how much do you allow the model to take into account your prompt and not to be more free in decisions. To tell him, I want you to really take a look on the prompt and make sure you follow it. Really make sure you follow it. So let's see. First of all, I will get rid of those 2. I change it to clip -1 for now. And let's see what happened. I will start from 2. Okay, CFG2 20 steps, and let's see what we are getting. 2 mean the lower is mean that it has more freedom. The model has more freedom, and it doesn't have to follow the instructions of the prompt. So you can see it did something, which is nice. Now let's move it here, duplicate it, and give it 5. Okay, we still get the box with all those soaps or rocks or whatever, but we start to get more data around it. It means that we ask him to be more precise to our prompt. Okay, now I will give it 8, which is quite high. If you want really precision, you can give it 12, 15. It can get until 30 or something like that, even more. But I don't know if you need it. So let's take 8. Again, we duplicate it by Option or Alt in the keyboard and dragging. And let's see what is 8. Now it needs to really follow our prompt. Okay, so it's follow it much better. Okay, so you can see it's different, and the falcon gone. It's okay. Now let's give it 15. Okay, now it really track us, and technically the sync was gone. There is no sync anymore. There are only those soap on the box, etc. Let's see the prompt if it makes sense. Array of handmade soap. Okay, wooden dish, very nice. In the bedroom, okay. But do you see a falcon on this prompt? There is no falcon. There is only the word bedroom. Now it doesn't say it's supposed to be a falcon for water. But let's see. Here it set it when we were on 5. At 8 it was much more precise, so it's gone, and we have some kind of a sync. But look what happened here on the 15. Now it's much more fit to the thing that we asked for, and we didn't allow so much decision for the model. Okay, so if you want the model to be more precise to the thing that you want, you need to give it much more higher CFG, which is the guidance. Good. Now let's go to the next one, which is the sampler. Now let's go and see another 2 topics here, which are the sampler and the scheduler, which are exist here. Okay? The sampler is actually the algorithm that the model is using to use the latent image and to crawl inside it and to understand the data, and which help him to denoise. This is the actually the mathematics way to denoise the noise from the latent until it has enough steps done to compose the image. Let's break it down a little bit. So we have 25 steps, and we have how much we want to be. We want the model to use the prompt. 15 is very high. Let's make it 7. Now we want to give him different algorithm to do this action by looking on the latent image, which is the actual data, all the data of the image, the compressed data, which we now give them the model the playground to handle it. And so the sampler is going inside and by the model instructions denoising the image. Now the scheduler working with the sampler, the way they actually working together, that the scheduler set each step for each step that the sampler is working on, how much it can influence, and it's giving it's like a timer or another algorithm that will say this is how much I allow you to do in each step. Okay, so we have how tight it is, how many steps, how we crawl inside the latent itself, and in what is the time for each step to work on, we can work on, and how much noise we allow to work. This is the scheduler. Okay, so you are not supposed to get totally different images by changing the sampler, but let's try. Let's remove those images, and let's run. We are now run on this image. Let's build it. As before, we will have multiple images. So this image is generated with CFG 725 steps with the sampler name Euler. Let's take one of my favorites, DPM plus plus 2M. And let's move it to the next preview. Okay, look what happened. Things are different. It look on the latent a little different. We still have the same structure, but it's a little different. The window is there, the Falcon change. Even the soaps have a different structure. It's almost the same, like that one, you see it's the same, but there are some that was breakdown. You see, splitted. So it look on the image a little different. It didn't change it a lot, but it did change it. Now, let's give to another one, to another scheduler. That's it, the TDIM. Okay, and run it. If I will look on very close, I will might see differences, but right now I don't see. But I do see between those, that one and that one. It means that there are some that are look on the latent in the same way. But now I want to give you the one that we just used, and to take a scheduler, different scheduler. Let's see what happened. I will override that image because it's the same as that. And let's see if we do have some changes between that image and that image. Look, it's actually different. The sink is gone, the plant is gone, the stones are the same, almost the same. It's a little different here and there, but they are almost the same. The stones are different. And again, we just change the scheduler, the way the model crawling inside the latent using the sampler algorithm. Okay, so you won't get totally different images. Unlike if you change the seed, you will get a different image. Yeah, let's see what we are getting if we use those and just change it in one. So I can go back. Now we are changing the actual noise. Now we get totally different image. We change the noise. It means that the beginning, the starting point of the model not the same anymore. If you go back, as we said before, if we give the same values, which even if they are random values that we are getting in this each time with the same model and the same everything, we're supposed to get the same image each time. And this is what happened. The same image. Although the values are random. You can call them random, but they are not really random. Okay? The selection is random, but when you select them again and again, you get the same one. So I want to summarize a little bit. So we said that seed, it's a different starting point of the image, which is the thing that gives you the most change in the image, because the starting point is totally different. The steps is giving the model more steps to check and to refine, to make a denoising on the noise that it get in the latent image by the seed noise. So as you get more and more steps, you get the image more and more refined. You will become better and better in details. CFG is giving you you are giving the model more freedom. As the number is low, you will give it more freedom to do whatever he thinks is the best. As you go up, you're the boss, and the prompt is more, and the model will track the prompt much better. The sampler is the algorithm that using to denoise the data by the model. Okay. The scheduler is allowing, by the way, the sampler, as we said, the amount of steps in each step we will do denoise by this algorithm of the sampler. The scheduler determine how much denoise and what is the scheduling ticks, the timer of the sampler can denoise in each step. Now we are going to the next point. Denoise. What is the denoise? Technically, is how much you allow the noise, the model, to denoise from your image. 1 is the maximum. I allow you 100% control to reduce noise from the entire image. Okay? In the current state, we have the preview image, which is the basic latent, the empty one, and the one with noise, right? Now, from this, we get an image, but everything here is noise. Everything. But if I will give it now, let's take this denoise, duplicate it again, and let's give it noise of 80. Okay, what is happening? We allow the model to use 80% of the image noise. Okay, and you can see that it generates a different image. Now, if I will give it 0.5, it's going to be even more different. See? There is a problem here. What is the problem? We tell it we allow you only 50% of the noise, but everything is noise. So what about the other 50%? Let's see. Let's see when this method is the best value for us. Let's see it together. So we are generating the same image. We're supposed to get here the same image. Right? It's the same image, the same parameters, everything is the same. This is good. So we can throw this one. Now I want to do a different method. I want to take this image. Let's say it's an image I took from somewhere. I want to take that image and to manipulate it. Okay? I want to use that image as the latent of the sampler. How can we do it? Let's see. Let's copy. 1, 2, 3. Okay. Control C, Control Shift V. Now we copy all the three with the connection, and with Shift we drag. Okay. So now we have another set of the same of the same nodes. Now, if I will run it, I will get the same. I will get the same result, because it's the same noise, the same everything is the same. But if I will now take the image out, do encoder, and give it that latent now, that is the final latent from the K-sampler, and give it to the image, to that image, and now I will run it, it means that now the K-sampler have the model positive, negative, everything is the same. It just I'm allowing it to take the last image as a latent, okay? And we, of course, we need to use the VAE. And let's run it. So now we have a K-sampler that's running on a K-sampler, on the result of another K-sampler. Okay. So what happened? We have a different image. A little bit different. You can see all the stones have a different. This is more marble, if I'm not mistaken. And here is more stone. So and the soaps are different. Most of them are different. Have more item. The wood is different. Okay. So it's took the image and technically it changed it. It gives us a new image by that image. Now let's copy it to the side and let's give it 0.2. Now the K-sampler allowed the model to change only 20% of the image, only 20% of the noise. Okay, so let's switch them and let's see what is the difference between the original image and the new image. Let's see. So we do have slice of changes. You can see here the stone is different. Okay, you can see that leaves outside, it's a little different. You have a little more noise here and there. The soaps are the same. But if you will look close, you will see that they have a small changes. Here you have a little dirt that you don't have here. Or here you have a line that you don't have here, etc. Small differences, because you allow only 20%. So if you have an image and you want a variation of it, and you don't want to lose it, just give that image, as the image is the input, give it like 20 or 30%. I want now to do it again, but now with 70%. So I allow the image, the sampler, 70% control of with noise on the result when the input is that image. Look what happened. Let me put this on top of that image. Look what happened. Now you can see the differences. You have here totally new things. You have it's still stone, but it's like breaks or something. The leaves outside is totally different. You have here some dirt. Okay, everything is the same idea. The same idea, but it's different. So you can get a different variation of the same image by giving the image as the input. And this is what the denoise is all about. Giving you control of the amount of noise you allow the model to use when it refine it. So if you give it an image of a woman or a man, you can get the same position. Everything is the same if you will give it 80% or 70%. You will get a different characteristics inside. If you give it 90%, let's see what happened. Let's give it 90. That was 70, right? Let's see what about 90%. 70, 90. Let's see. Okay, here the marble, if you remember from that one. We are very close to that image now. But it's a little different. You have the signs are different. You see? So it's all about noise. All about what noise you allow to the model to use to get the image, to get the image from the noise. We just get to the last section of this video, this tutorial. It was quite long if you get to that point, and I hope you have a quite decent understanding about each part of the Comfy. So thank you very much. Subscribe, like, assist me to spread the word. See you in the next tutorial. Bye.